Howdy, my presentation title is High Strain Rate Indentation Response of Nickel Cobalt Vanadium Medium Entropy Alloy. The work was in collaboration with Dr. Ibrahim Karaman's group as well as Dr. George Farr's group at Texas A&M University. The research was funded by the Army Research Office with the program manager Dr. Daniel Cole. Before going to the scientific part of the presentation, I'd like to quickly share with you the motivation of the work, why we are interested in the dynamic behavior of materials. I took the description from Professor Mark Myers' book, Dynamic Behaviors of Materials, and the images were actually created by Dao Li. Assuming you bring a dagger or a blade to a beach, not saying that you should bring a dagger or blade to the beach, assuming that happens, and if you slide the blade slowly into the sand, you can actually do that quite easily. In contrast, if you have a bullet hitting the sand at a very high speed, the sand can effectively block the bullet. In fact, in the First World War and the Second World War, people actually used sandbags to block bullets. And this example is a really good illustration how that sand can behave quite differently when you deform it at either a low strain rate or at a high strain rate. The change of mechanical properties in response to the strain rate is referred to as the strain rate sensitivity. And the strain rate sensitivity can also be widely observed in many FCC and BCC crystals. In the example on the left, it's a FCC metal example. On the x-axis, that's the true strain. On the y-axis, that's the true stress. As you increase the strain rate, the yield strength does not change dramatically, but the strain hardening behavior changes. At a given strain level or plastic strain level, you will see that higher strain rate will lead to higher flow stress. For BCC metals, it's a bit different. As the strain rate increases, the yield strength increases, but the strain hardening behavior does not change. But regardless, you'll still have a similar observation that a higher strain rate will lead to a higher strength. We will pause here for a little bit and try to understand the classical understanding of the strain rate sensitivity in FCC and BCC metals. In FCC metals, a higher strain rate will lead to promoted dislocation multiplication, so you end up having more dislocations in the deformed volume, and that leads to Taylor hardening. That's why the yield strength does not change, but you have more pronounced strain hardening at high strain rates. For BCC, it's a different story. The yield strength is governed by the pyro stress of the metal, and the pyro stress of the metal increases as you increase the strain rate. This is why you see an increase in the yield strength as the sample is deformed at high rates. The strain hardening remains more or less the same. The conventional way to obtain the dynamic behavior of materials is to perform either Kolsky bar tests or plate impact tests. I took the image on the left from the NIST website and the image on the right from the Hopkins website. As you can see, in both setups, they require a lot of room, a lot of lab space. In addition, from each test, you get only one data point. So this is a pretty effort-demanding technique, as well as that requires a lot of lab resources. At Texas A&M University, in Professor George Farr's lab, they designed a new high-strain rate nano-indenter testing system. On the left, that shows the schematic of the instrument. The size of the instrument is about like stacking two microwaves, so it's more like a desktop setup, so that saves a lot of space. The second thing is, since we're doing nano indentation tests, from one sample you can get many data points, so we can consider that as a high throughput technique. During the high strain rate nano indentation tests, the tip is pulled back, and once released, there's acceleration to the tip, and when the tip is about to reach the surface of the sample, it reaches the maximum speed. During this test, since eventually like the tip will slow down and reaches speed 0, so the strain rate is varying, And what we calculated here, or what Dr. Fa's group calculated here, is really the average strain rate or average indentation strain rate. The figure in the middle that you can see here is a depth load plot. And in all the tests, they stopped at the same depth. The model system is a 111 aluminum single crystal. As the strain rate increases, the load to achieve the same depth also increases. What this tells us is at a higher strain rate, the hardness is higher. Aluminum is FCC. The same observation was also made in the BCC moly. As the strain rate increases, the load that is required to achieve the same depth also increases, which is manifested by a high hardness. These two examples show that the strain rate sensitivity was a common observation for both FCC and BCC metals when they are subjected to the high strain rate nanoindentation. The next thing Dr. Fa's group went to do was the reloading experiment on the dynamically indented area. The aim is to check whether the mechanisms observed in the bulk samples can be also replicated or reproduced in the high strain rate nanoindentation tests. The design of the experiment was elegant and the results were exciting. In the case of aluminum, after the impact test and straight after that when doing quasi-static or low strain rate indentation, they observed an increase of hardness. What this tells us is that the high strain rate nanoindentation indeed introduced more dislocations in the deformed volume, and you have tail hardening here. In contrast, for the dynamically indented moly, which is BCC, after the impact, although the hardness during impact is very high, when you deform or when you do another indentation in the deformed volume, the hardness remains the same as the low strain rate deformed indents. That tells us that the increase in hardness was a result of the pyrostress. Both the aluminum and the moly examples show that there's really good agreement between the nano indentation, high strain rate nano indentation results and the bulk dynamic testing results, which came to me, to be honest, as a pleasant surprise. These results also suggest that high strain rate nanoindentation can be used as a high throughput method to quickly obtain the dynamic behavior of different material systems. Now let's move to the medium or high entropy alloy systems. Why the FCC medium and the high entropy alloys are interesting. This is because in terms of the crystal structure, they share the same FCC structure compared to other FCC pure metals. Interestingly, because of their lattice distortion, the lattice friction part is similar to the pyrostress people discuss in BCC metals. Therefore, the medium and high entropy alloys are of interest to study their dynamical behavior. The model system we used in this study is the nickel cobalt vanadium medium entropy alloy. This sample we obtained from Dr. Karman's group. From XRD, you can see a strong 200 peak that tells us this single crystal has the 001 direction aligned out of the plane. This was confirmed by the EBSD results from the IPF. You can see there's only one color, it's reddish, and it tells us it's close to 001 direction. It's also confirmed by the pole figure. The 001 direction is only a few degrees away from the out of plane direction. We further performed the EDS to look at the chemical distribution. For nickel, cobalt, and vanadium, there's a uniform distribution telling us there's no presence of the second phases or there's no chemical segregation. Before performing the high strain rate nano indentation, we started the work by doing the low strain rate indentation and using the results as the baseline. In the figure on the left, this is the classical Nick scale model when looking at the indentation size effect. On the x-axis, that's 1 over h. H is the indentation depth. The y-axis is hardness square. The blue curve you see here, or the blue dots you see here, these are the results from the medium entropy alloy. You can see the slope is pretty high. It's about 3.98. This is much higher than the 1.22 from the moly as well as the 1.05 obtained from nickel. What this tells us is the FCC medium entropy alloy has a strong indentation size effect. The strong indentation size effect is also reflected in the figure on the right, which is the log H, the displacement, and H, the hardness curve. This approach has been adopted by the micropillar community, and the slope tells us the dislocation mobility. In general, FCC crystals have a higher slope than BCC crystals. In FCC metal crystals, during the onset of nanoindentation, the generated dislocations can easily travel down into the material, leaving behind a relatively defect-free volume that requires high stress to activate new sources. In contrast, for BCC metals, during the onset of the nanoindentation, dislocations are less mobile, and the dominant mechanism for plasticity is dislocation multiplication, and that's why the BCC curve, the BCC lines, they have a lower slope compared to the FCC crystal. In this example specifically, the nickel cobalt vanadium medium entropy alloy has a much steeper slope compared to both the BCC moly and FCC nickel, and in a few slides you'll see why this is the case. Next, we performed the high strain rate nanoindentation. This, I would say, is the most important slide for this presentation. On the left, you see the indentation depth and the load curve. There are two sets of data plotted in blue and in red. The blue curves are from the low strain rate indentation, and the red curves are from the high strain rate indentation. The strain rate, indentation strain rate for low strain rate indentation experiment was 0.01, and the average indentation strain rate for the high strain rate experiment is 11,000. At the same indentation depth, higher the load tells us higher the hardness. If you just qualitatively compare the red curves and the blue curves, you don't see a huge difference. And converting the data into hardness, the low strain rate hardness was 3.46 plus minus 0.06 gigapascal. The high strain rate hardness was calculated to be 3.58 plus minus 0.04 gigapascal. Although the difference is statistically significant, but the increase is marginal. It's a barely 3.5% increase in hardness. On the right are the confocal microscopy images showing the surface information of the low strain rate and the high strain rate indented volumes. A quick comparison showed no obvious differences. In both cases, we also saw those band-like structures. And using TEM, we'll see what these band structures are. Next, let's compare the results we obtained in the nickel cobalt vanadium to aluminum and moly. For the nickel cobalt vanadium medium entropy alloy, the hardness difference is 3.5%, which is very small. For aluminum, the strain rate is 4,000, not as high as 11,000, and the hardness is 35% higher. In moly, it's the same strain rate in the high strain rate indentation experiment, and the difference is as high as 56%. So when you compare the nickel cobalt vanadium results to aluminum and the moly, it's just so small. And why this is the case? To understand the lack of the strain rate sensitivity in the nickel cobalt vanadium medium entropy alloy, we performed TEM and TEM based characterization. In both cases, we saw those band-like structures, and we identified those as slip bands. When those slip bands are aligned parallel to the electron beam, they appear to be those bands. When they're aligned at an angle to the electron beam, you can see the arrays of individual dislocations. These features are common in both the low strain rate and high strain rate indented samples. When these bands terminate on the sample surface, they give you the slip traces. That's what you saw previously from the confocal microscopy images. We further performed precession electron diffraction, PED, on these two samples, and in both cases you can see it's still largely single crystal. There are no twins or phase transformation activated. These results indicate that the planar slip of dislocations is the predominant deformation mechanism in both the low strain rate and high strain rate indented nickel, cobalt, vanadium medium entropy alloys. You may wonder why the planar slip of dislocations in this alloy is able to contribute to, first of all, the strong indentation size effect, and secondly, the low strain rate sensitivity. In planar slip, most dislocations are confined within those single slip planes. There's limited cross slip. Without cross slip, there's reduced or limited dislocation entanglement. During the onset of the indentation, dislocations can easily glide deep into the material, leaving behind a relatively defect-free volume, and the dislocation starvation mechanism is pronounced, and this is even more pronounced compared to the regular FCC crystals, in which cross-slip is more common. And this explains the strong indentation size effect in nickel, cobalt, vanadium medium entropy alloy. The low strain rate sensitivity in nickel, cobalt, vanadium can also be explained by this planar slip behavior. For the regular FCC metal crystals, the high strain rate sensitivity is a result of dislocation interaction, because at high strain rate there are more dislocations generated. In the case of this medium entropy alloy, since the dislocation slip is largely planar, there's limited dislocation interaction, thus there's very limited Taylor hardening. We'll only see pronounced strain hardening when those slip bands are intersecting. Moreover, because the nickel, cobalt, vanadium medium entropy alloy is FCC in nature, although there's a lot of lattice distortion, the lattice friction is not as high as the BCC metal crystals. That's why there's no strong strain rate sensitivity observed in this material. There are a few takeaway messages from this presentation. The first is the nickel, cobalt, vanadium medium entropy alloy exhibits low strain rate sensitivity. The second is the low strain rate sensitivity could be explained by the planar slip of dislocations, which is kind of unique to this type of medium entropy alloy. Then such an insight may be also extended to understand the dynamic behavior of other alloys in which the planar slip is prevalent. That is to say, if you have an alloy system, if the stacking fault energy is not low enough to activate deformation twinning and the transformation, but also not high enough to promote cross slip, you will also see low strain rate sensitivity. And this concludes my presentation. Thank you very much for your attention.